Hey everybody, and welcome to another episode of Space Science with Python. Last time we created an interactive widget where we were able to plot the detectable NEOs in the night sky, adjusting the apparent magnitude, the absolute magnitude, and also filtering out the objects that are a little bit too close to the sun, and also able to distinguish between the certain NEO classes. Now we got some ideas and impression for which classes and objects the opposition effect was quite prominent and where everything was more uniformly distributed. So this was kind of nice to get a feeling or also understanding where these objects appear in the night sky. But remember, what is our objective? We want to create some kind of simulation tool where we can at the end say, okay, 80% of NEOs can be detected within a certain time frame if you have a limiting magnitude of your telescope of XYZ. And this is something we would like to start today. So today we will start with our detection simulation tool, and it also goes into the assignment a little bit from last time, where we also compute all objects depending on the observation time. Now today we will only focus first on the known NEOs, and then also integrate them over time using the limiting magnitude. But in the next episode, so the last episode of this episodes of this year, we will use also a simulated NEO population, because our NEO data are probably maybe biased because of the observations that have been conducted. And of course, we would like to model the telescope. Now, modeling the telescope is something we will do only in one video, and then the model is something we will do also in another video, and then we are basically done with the project. Today, we will start creating the small detection simulation program, and the next time we will see if we have some kind of bias effects in our data or not. So this is a very simple Jupyter notebook, notebook number 10. You will find this in the repository, and we can see that we have here only a few cells, and we can go through the cells step by step. Now you see I already executed them. Maybe I should first clean up all the cells so that we can really start from the beginning. And let me just also restart the kernel. Now, first cells are something you have already seen in the last videos: importing libraries, calling the NEO database, extracting all the data, and then also calling some spice kernels here in cell number 3, and then also converting it the values to in kilometers, radians, and so on. So that can be used for spice. And this is basically the 4 cells that we already created. Now, cell number 5, we would like to make now some kind of simulation. We want to integrate over time, right? So we would like to have a starting point of our NEOs. We use the starting time in 2000 this year, January 1st, and then convert into ephemeris time. We would like to focus first exclusively on the opposition direction of the sun. So this is our area where we observe our NEOs. And I would also suggest not to observe the entire night sky at once. So let's only focus on the opposition direction, and also only in a circular region 15 degrees around this opposition point. So this is like the area that we observe simultaneously, let's say. Yeah, it's quite unrealistic because it's quite huge, but you can also adjust this here if you want. We can now set a minimum detection threshold. So let's say every object that is brighter than 26 magnitudes is then observable or will be classified as detected. And all detected NEOs are then put into a data frame. Finally, we will also create some kind of step size for our observation. So we say, okay, here first, we only want to observe for 8 hours. So starting at the 1st January, only 8 hours. And then in a time range, or each step is like 3,600 seconds, respectively 1 hour. Now we can go here into the next cell. First, I should, of course, execute cell number 5, and now cell number 6, which is our simulation. And here we really iterate through all the time steps, so step by step by step. We add the time here in seconds, the ephemeris time, and then we also append the ephemeris time to the NEO data frame. We are then computing the different vectors that we already did last time. Like, for example, the sun to the earth position vector, earth to the sun. By inverting it, we then put the sun to Neo position, then the Neo to earth position. So all the vectors we did in the last video. So I would suggest to take a look at the last videos, because we need vectors that can be used to compute the apparent magnitude now here in this part. So here is where we computed the apparent magnitude, and then afterwards we are then also adding the angular distance between the opposition direction and the NEO in the night sky. Afterwards we can then see what kind of, which NEOs are detectable by filtering out the data frame. So we say, okay, if the apparent magnitude is smaller than our threshold, and also the angular distance to the opposition direction fulfills a certain criterion, then we have like our detected NEOs that are then appended or concatenated to our detected NEO data frame. And of course, the detected NEOs are then removed from our original data frame. So over time, we have less and less NEOs to compute. And in case we have, detected everything, our for loop, breaks out. So we do not continue computing any positions anymore. So let's start this one here. And we see, of course, if you make some numerical simulations, programming languages like C or so are way more powerful than Python. But here everything is, it's way slower, of course, but maybe more explainable. And we also use it now here for 8 hours or 8 observation hours. So you can here adjust now in cell number 5 all parameters that you like, so that at the end we have here converting our time of detection into UTC frame, so something that is human readable. And then after filtering all the data, we can then store our results into a Parquet file, and the Parquet file is stored in results data, and then number 10 for our 10th session. And the file name is then, the file is a quite long and complex file name, but it simply contains all the simulation parameters configurations that you request. The point is, of course, here the parameters of the simulations here and also here, it is more like, best practice not to hard code it in a cell, but more write something like configuration files or so, and then read in the configuration files, and then execute the simulation based on your files. But here we just start with our simulation, so let's keep it hard coded in cell number 5. And then at the end you can then see what kind of NEOs here have been detected. Now we have 300 NEOs within this 8-hour time range. And until next time, I will then execute for a larger time frame, maybe for a year or so. And then we can take a look what kind of NEOs are detected easier or faster than others. This is of course biased, because it is maybe our detected NEOs are already inherently biased by the telescope service and so on. But it doesn't matter, because with the same simulation we will apply to simulated NEOs. So I will search for a simulated NEO population. I already know one, the Botke model from I think 2018 or so. I will show it to you next time. And then we conduct the same simulations for the simulated data set, and then see how this goes. But again, in our next video, next week already, we will just take a look at the detected, or we take a look at the results of our simulation and see what kind of NEOs have been detected. Just start to play around a little bit with the simulation parameters. Maybe you can already start with your own analysis of the results and see what kind of NEOs are way easier to detect than others. Feel free to do so, and I would suggest that until then you play around, and I prepare the next session for next week. And until then, see you next time.